Hello everyone, in this video we will go over some properties of summations. Specifically, I'm going to go over each one of the 8 equations that you are seeing on this page. As you can see, I won't be talking about summations with limits, but I'll go over some basic properties of summations that can come in handy. As an example, summations are used a lot in data science. Okay, let's first briefly talk about the summation in its most basic form. Here, you see a notation involving summation. So this notation means that we'll be adding a sequence of xi's starting from I equals 1 all the way up to I equals n. In other words, this notation is equal to this sum where you simply add n number of xi's. So as an example, x1 can equal to 3, and the last term, xn, can be equal to -5. If you add all of them, x1 all the way up to xn, then that sum is what this term or notation represents. Okay, now we have the addition of 2 summations. It's easy to see that this addition of 2 summations is equal to this term where you have sum of all xi's and yi's. So we're going to add x1 all the way up to xn, and then we're also going to add y1 all the way up to yn. And all of this is now going to equal to this sum where we have x1 plus y1 plus x2 plus y2 all the way down to xn plus yn. So as you can see here, compared to the first line, I just rearranged the terms a little bit. And now we can express this sum using this notation. So the bottom line here is that this term equals this term over here. And the same logic applies when you have a subtraction between 2 summations. Okay, so that was the first property that I wanted to show about the summation. Now we have a different property. Now we have some constant c multiplied to the summation of xi's. So c can be any number, right? 0.5 or -10 or some other number. We can see that this is going to equal to c times the sum of xi's, which is then going to equal to this term over here. And finally, we can express this sum using this notation where the constant c is brought into the parentheses and is now a part of the summation. So the main point here with the second property is that this term over here equals this term. Now we are going to show that the summation across a constant c from I to n is simply going to equal to n times c. Maybe you're finding this a bit weird because c doesn't have any I subscripts, right? But there is nothing wrong with this equation, you just have to take it for a fact. To give you my own explanation as to why we get n times c, suppose we have x1, x2, all the way up to xn, and they are all equal to c. We can then say that xi equals c for any I because all xi's are equal to c. Now, if we sum over the i's to both sides of the equation, then we're going to get this equation, right? This then also means that this equation is true. I just simply expanded out the summation for the xi's. And since all xi's are equal to c, we finally get this equation. And so therefore, we can conclude that this equation is true. Here, I'm going to show how this summation is related to the mean or average of xi's. So first, this term is equal to this sum, as we already know. Now, to this sum on the right-hand side, I'm going to multiply and divide by n, so that we can say that this sum equals this term. Here, note that the term inside the parentheses is the mean or average of xi's, which means that we can say that the sum of xi's is equal to n times x bar, where x bar is a notation representing the mean of xi's. In this page, we're trying to differentiate the term inside the parentheses with respect to c. Note that this equals this term here on the right-hand side, where I simply expanded out the summation. Now, the differentiation operator can go inside the parentheses like this. So finally, we can express the right-hand side using this notation, and all of this means that this term over here is equal to this term. So the main point here is that the differentiation operator can come inside, and you can differentiate even without expanding the summation, which can make calculations simpler in some applications. Let's now go over an example of this problem in this page. Suppose f of c is c squared. And that means that the particular summation that we're trying to deal right now is this one right here, where instead of the f of c, we now have c squared. So here we want to differentiate with respect to c, the sum of xi's multiplied by c squared. Well, since the differentiation operator can go inside the parentheses, we have this term on the right-hand side. And now if we differentiate c squared times xi with respect to c, we'll get 2 times c times xi, so we'll end up with this term on the right-hand side. So the main point here is that differentiation can be part of the summation, and you can differentiate even without expanding the summation, which can make calculations simpler in some applications. I have another example here. What do we get if we differentiate the sum of xi's with respect to x1? Well, again, the differentiation can come inside and be part of the summation. But here, you have to be careful before differentiating this term and jumping into conclusions. For this problem, to make everything clear, let's first expand the summation so that we get this term on the right-hand side. Now it's easy to see that the only term that's not going to be 0 is this first term. Everything else will be 0. So the final answer would simply be 1. I just wanted to show this example because yes, the differentiation operator can come inside and be part of the summation, but sometimes you need to be careful before carrying out the differentiation. Okay, here this equation is showing that in general, the multiplication of two sums, one for x and one for y, is not equal to the sum of multiplication of x and y. You can make up some numbers and try it yourself. Here you see that in general, the division of two different sums, one for x and one for y, is not equal to the sum of x divided by y. And finally, this page is showing that a sum of xi's raised to the power of a, the entire sum raised to the power of a, is not going to equal to the sum of xi raised to the power of a. So as an example, in general, square root of the entire sum is not the sum of square root of xi. Okay, these are all the properties that I wanted to go over in this video. And keep in mind that there are more properties involving summations that are far more complicated. But the ones that I went over in this video should get you started in the right direction.